Thanks. Okay, let me introduce our today's speaker. This is Professor Tsai-Wen Wen from the PKU, and this is our big pleasure to hear and to see so great professor in our seminar with interesting topic about automatization of the scientific research, and not even just scientific research, but research in optimization. And yes, please, Simon.
Yeah, thank you very much. So I need to share my, okay. So can you see my screen?
Yeah.
Okay, no problem. So, uh, so today it's my great pleasure to give a presentation in Professor Alexander's seminar. So thank you very much for the kind invitation. So today I'm going to share my own experience on designing learning-based algorithms and theories for mathematical optimization. So this is a joint work with my students and also a few engineers. Um, so let me start from The Bit of Nathan by Richard Sutton. Have you ever read this article? So if not, probably you can Google this title, The Bit of Nathan. So it's an unpublished article from Sutton, and written dates back to 2019. Um, I read this one a few years ago, and ever since I think this is a great encouragement for learning-based algorithms. So let me start to summarize a few key points of him. So he mentioned the biggest lesson from 70 years of AI research. So general methods that leverage computation are ultimately most effective and by a large margin. He give a few examples. Most of us know um, for example, um, the games, both the chess and the Go game, right? So the expert rules, so strategy based on expert rules and the strategies are surpassed by reinforcement learning. Um, so on and so forth. There are many other successful stories. So for all these stories, he said we should learn about is um, so what kind of approach should we design, should we develop? So those one which can scale with increased computation. So how those methods can scale arbitrarily? There are two words, keywords. One is search, and another one is learning. And for traditional research, for example, I'm doing optimization, most constrained and unconstrained optimization problems. We are very good at designing, for example, gradient type methods and Newton's type method, and so on and so forth. So those are about search. But what we do not do traditionally is learning. How can we learning algorithm from data or from problems we have solved? So ever since I think my the research in my group are focused on those two keywords. Okay, so today I'm going to share you a few scenarios. Um, so let me start from unconstrained optimization. Um, so traditionally, how we solve a given optimization problem, right? So there are many types of problems. For example, unconstrained problems. Even unconstrained, we have quadratic optimization, right, or non-smooth optimization, and we have linear programming, quadratic programming. So for a given problem, we usually choose a algorithm and, based on the structures of the problems. And then usually we, in a particular application, And there are many instances, and for each of the instances, we have repeated this process. Right? So for each of the problems, even those instances are very similar. The data or the structures are very similar, but we have to repeat. Um, so that's what we do in previously. But nowadays there's that we have lots of data, and in particular for example in industry, for example in scheduling or many other applications. What people do is for a particular problem, the mathematical model is the same, but the data is different. In other words, they have to repeat those kind of things, the problems, day by day, right? Even tens or thousands of problems we have to solve them. So the question is, given this kind of data, can we uh, can we design algorithms which can learn from the data? So for example, we solve problems on a given data set, and then given another problem whose structure is very similar, can we accelerate the solving process, right? So then the paradigm in machine learning probably is very encouraged. In machine learning we have training and then we have testing, right? For training, we can training a learnable algorithm and training the parameters, and for a given data we just pass the data to the model, and then we obtain the solution immediately. So we um, can we do this kind of process for optimization? So today, let me start from a very simple scenario. I guess most of us are familiar with the gradient type method. So we're going to minimize the function. Suppose we uh, say, compute the gradient and take a step size, and we uh, update the iterations, right? And we usually will have many iterations. So traditionally, so this parameter have to tune based on our experience or by certain kind of algorithm, for example, various types of non-search algorithms. But my question is how we learn this parameter from no data. Similarly, there's another algorithm called the nested exploration. The exploitation step for this kind of parameter can rename both the step size and this parameter for another data. So if we call this algorithm the discretization, so for this gradient type method, we can arrange the items, move xk to the left-hand side and divide by eta, and then eta goes to 0, they obtain ODE. And similarly, for this natural algorithm, we can obtain a second order type of ODE. So generally speaking, there's a correspondence between ODE and the discretized algorithm. So it's very difficult to learn the parameters from this discrete algorithm, but what we can do is we can learn the parameters of ODE, and then with discretize ODE, we can obtain the parameters. Okay, so let me show you this figure. This is a overall pipeline of algorithm. So we want to learn the parameters from the data. Then we construct a machine learning problems. So I will explain you later. But the goal is for a given data set, we have to minimize the total number of iterations, which is we call the stopping time for the ODE. But essentially, the total number of iterations. And under certain kind of conditions, for example, the ODE should be stable, and the ODE should the algorithm should converge. Okay, And then from the data, we can we parameterize those alpha and beta and gamma, and do the training process. Once we train, we obtain the parameter, and we discretize the ODE, for example, by explicit O9 scheme. And then we obtain this kind of discrete algorithm, and hopefully in practice, in the testing data, and those performance can be much better. If you want, to check, you can test our algorithm at GitHub. So let me go into the detail a little bit. I've already just mentioned for this kind of ODE, second order type ODE. So let's suppose those kind of condition is satisfied, then we will have the function value of xt minus x star. This is the optimal function value is of order 1 over delta t. And so this is so-called the convergence condition. So then we so in the machine learning problem, so we have to put the conditions of this one into the constraints. Okay. So and what is the stable condition? This is another example. For example, we solve the ODE by the ONA type of discrimination, and if we do not control the step size, and after, for example, 175 iterations, the iteration may blow up. So then we have to control the parameters. Other words, control the size of alpha and beta t and gamma t. Those have to satisfy those kind of condition. Um, those conditions, if those conditions are satisfied, then we, for the discretized, so this xk is for the discretized algorithm, and this one is the trajectory of the ODE. So what we only need is a discrete version of the algorithm, and under those conditions we can ensure the convergence, and also the complexity is still 1 over k. Okay. So what is object function values? So for the given problem, what we need is when we solve the problem, we want to ask the norm of the gradient should be smaller than epsilon. And the capital XT is the trajectory of the ODE. Okay. So we have to we define so-called stopping time. Stopping time, the first time t such that this stopping time is this norm of the gradient is smaller than epsilon. And for the discrete algorithm, they simply the number iterations, right? So I just summarize for so for a given data set. So what we need is we minimize the expression of the stopping time and under convergence and the stability conditions. So for a data set, for a given ODE, then we construct a machine learning problems to find a optimization algorithm, and hopefully in practice it can perform much better. So this we do some experiments on the knowledge regression. We have tested a few examples. You see this is traditional gradient descent method, and this is this this corresponding to, so the blue line corresponding to the Nestov acceleration gradient method, and the red one corresponding to our learning algorithm. And this one I can see actually is also a learning algorithm, but it's a different approach. So we can show in our approach, in this way we can output the other competitors. So most recently we are also trying to extend this scenario to constrained optimization, for example, linear programming quadratic programming, and the performance is also very promising. The major difference is we have to change the ODE, the change ODE to a different type, which can which is derived from, for example, the primordial algorithm for linear programming and so on and so forth. Okay. And then, so similarly, you can develop, design certain kind of loss function and certain kind of constraints, and then you can obtain similar results. So this is the first part of my algorithm. And so if you have any question, just stop me anytime. Okay. Mm. So next I will
Maybe I
I
can ask.
will
Yes,
yeah,
sorry.
yeah, sure,
Maybe I can
sure,
ask.
sure, please,
Is
please.
this learnable algorithm is universal or just for you need to tune on every data set?
This is a very good question. So it depends how you parameterize those things. If those do not depend on the data, then it's not universal. For every data set that you have to train it. But actually, you can develop kind of much more complicated parameterization. For example, this should be depend on the given structure of the problem. So I think then it can be very general.
And the question, maybe you try this. For example, you
Mhm,
just train on different, very big synthetic number of the tabular data set, tabular data.
mhm, mhm,
Train on this, find some good method, and
mhm.
try this method on the new data set. Is it
Uh-huh,
work or not? Is it like kind of property of fundamentality of this method?
uh-huh. You mean the generalization?
Yes. Yeah.
Probably not. Probably not. So what we now we do is only for the logistic regression, and what we do is for small data set. So why? So there are so in this work actually there's certain kind of shortcomings. If you take a look at those conditions, in particular for this one, this is the eigenvalue of the Hessian,
Mhm.
right? Um, so so for those things, they have to put in the constraints, um, and then for the machine learning algorithm. So for this problem in itself, right? For this problem in itself, we still have to compute the gradient of the object functions, also the constraint. For this one, it's very interesting. Let me ask you a question. So now you say this is so-called stopping time, right? And for a discrete algorithm, this one essentially is the number of iterations. So what the parameters? The parameters are those things, are alpha, beta, gamma. So my question is, um, do you believe that the number of iterations is a function of beta and gamma? Can the num iteration is the iteration differentiable uh, with respect to beta and gamma t? So this is a very interesting question. So in this work, we analyze, we've actually given the conservative gradient, subgradient of the stopping time. In another work, which was published at the NIPS last year, we analyzed for the discrete algorithm, and so there are many other questions. Because of the subgradient, you see, and in the constraints, there's the eigenvalue of the Hessian. That means we have to compute the third order the derivatives, which can be very prohibitive. It's not maybe it's not possible for huge type of data. So in this sense, we probably we need to revise those conditions. We have to develop new models which is suitable for large scale problems. So I think it's for this is a bottleneck for this work.
I see, I see. But if we fix that logistic regression, but
Mhm.
say let us change the data sets,
Yeah,
only
yes.
the data sets, yeah.
Yeah, I think this is a very good question. That means in the data set this F what is the data set? Data set is a functions, right? So you just connect different function object functions, and I think what you ask is what's performance on another data set. I think we have to train on the other
Yeah.
kind of data. Yeah, yes. Uh-huh. But now, because our parameterization is very simple, simple neural networks. So we have to try large data sets.
Yeah. Yeah, I see, I see, I see.
Okay, so thank you very
Yeah,
much.
thank you, thank you, thank you. Yeah.
Mm. Uh, so next, let me move to uh, another another different kind of scenarios. Um, So the goal now is different. Um, we want to find a foundational model optimization. So particular here, our goal is for combinatorial optimization. But I think the idea probably can also extend to continuous optimization problems. So here is my foundation model. Right? So traditionally, this one we for a given problem we develop certain kind of algorithms, but in this new scenario, we no longer treat the variable as a variable, decision variable. So we jump on the variable from a kind of distribution, and so ideally this for this distribution for this sampling x should be feasible. But it's highly possible. Maybe for complicated problems may not be feasible, but we have different kind of strategy to handle this case. So far, let's assume we can develop a design very good sampling procedure to obtain feasible solutions. And then, um, so instead of minimize this function, we minimize the exploitation of this one. And so what's the foundation model? We have additional exploitation. So we can sample the function f for different types of problems. Suppose we construct a sufficiently deep neural networks for this distribution, and I suppose we can connect a sufficient large number of data sets, uh, sufficient number of problems, then and then probably we can obtain a foundation model. That is say. So similarly for the general, for example, for ChatGPT, you ask a question and it will was responding, provide you a answer immediately. If you do not satisfy this solution, you can repeat this process, right? Pretty quickly. And now suppose we can do the sampling. So sampling can repeat very pretty quickly, right? So we feed the data and we want to obtain the solution immediately. We know for if the if the number of variables, if the number of constraints is huge, it might take a few hours or even a few days to solve a single problem. But now we want to obtain a solution in seconds, in minutes. So is this goal feasible? So today, let me show you a few examples. Um, in the last few years, we have tried binary operation. This has been published at mathematical programming. Also, the routing problems we have published at ICOR last year. We also developed algorithm for training, also scheduling, and quadratic assignment problems. And for the code, you can test it online. So let me start from the binary operation. Um, So we're going to minimize the function. The variable is binary, -1 or 1. Let me ask you a simple question. Uh, are those two problems? So are those two problems are equivalent? Okay. At least, for example, so here the variable is x, but here if we change the variable to be p, that means x is sample according to the p rather than p theta. So variable should be changed to p, and the p is a distribution, it is a probability. Then, for those problems, right, it's immediately the equivalent. So now, let us parameterize the distribution, and suppose the uh, suppose the approximation is pretty good, and we know I believe this one, the solution of this one should be sufficiently close to this one. Um, and for this setup, this is for a single problem because we do not have the extra one, right? And the explanation outside. So this is a linear algorithm for a particular given instance. So let me show you another example. I believe most of us have tried this game, the Tetris, right? So it's original from the Russian. Um, and so essentially, this game is a discretized optimization problem. A block is falling down. There are three actions we can make the decision. For example, whether we turn this to left, turn right, or whether rotate this block, right? So this integer, right? And and the decision is sequentially until the game is over, right? Is ended. That you have to make a decision at every step. But all the people you usually do is in reinforcement learning. So they no longer treat this as a discretized problem. What they do is they parameterize the action. The action is turn left, turn right, and make it rotate according to a certain kind of distribution. And of course they parameterize this distribution and solve this problem. You see, immediately you can see the similarity between those two problems, right? Uh, of course, there's another way to interpret this model. Um, so suppose we know all the integer solutions, the optimal solutions. So OT is the target distribution. So then suppose we know this distribution, then we can sample the optimal solution for all the feasible solutions, right? But of course, in practice, we do not. So the optimal solution are not known. We do not know the optimal solutions. What we can do is we know this so-called Gibbs approximation. Suppose the parameter lambda goes to 0, and this Gibbs distribution will converge to the optimal, the targeted distribution. So then a typical model in statistics is we can minimize the distance between the Gibbs distribution and the parameterized distribution. So p theta is the distribution we want to find, and then we minimize the distance between those two things. Of course, because they are distribution, we use the so-called Q divergence, and we plug in the expression of this Q nanta, we obtain this function. You see, for this capital Z, this is a constant. So essentially, the summation of all the feasible solutions, of course, this is a constant. And then you see, so this problem minimization of the KL divergence is equivalent to this problem. So the first time you say is so-called loss function. So this is essentially the same of this one, right? And the second thing is called entropy. So this is entropy. So this is regionalization. So we say, so this one is exactly the same to other machine learning problems. We have loss function, we have a regular relation. So now we want to solve this problem. We want to ask, can we compute the gradient of this function with respect to theta? By very simple derivation, we can check the gradient actually can be written in this form. So we define so-called advantage function, which is similar to the function in reinforcement learning. This is the function values simply, and minus a constant. This constant, the purpose is to reduce the variance. Okay. And the gradient is taken with respect to the p theta, right? So this is exactly the same as the Punnett gradient in reinforcement learning. So then it's very interesting. We see, so although this problem is very different from all the traditional reinforcement learning problems, right? Also different from the models in large language models, but the algorithm we say that all of them are Punnett gradient method, right? So in this sense, they are the same, and we can unify the modeling. Okay. So once we have the gradient, of course, we can do the stochastic gradient method, and then you can do a few small examples. Then you probably will say the performance probably is not very attractive. Why? Because this is a NP-hard problem, right? Suppose if you can do it very easily, this is contradictory to our common sense. So we have to do more sense to improve the performance. So here is our algorithm. So this is a pipeline. So for a given problem instance, we can parameterize the distribution, and then we can do sampling with respect to p to obtain k starting points. And for each of the starting points, we generate m Markov chains. So in other words, of course you can do it by very naive sampling. Simply do the sampling, and then you can repeat the process. You see, you can for the sample we can compute the advantage functions and also the gradient, and then you can update the parameters. Right? This is the simplest way to do. But there's structures because you see. In the optimization, this iterative algorithm, if we so usually there are a close relationship between two consecutive iterations. But if we simply do the sampling, then there are no combinations. So that's why we do the Markov chain sampling. And so for this iteration, we generate m Markov chain in parallel. And this k starting point for each of them will generate m examples. So this process can be do very efficiently in GPU. Okay, it can be done simultaneously on GPU. It can be do very quickly. And of course, again, this stage, you can also update the advanced function, update the gradient, but from our experience, the performance is not very good. So why? Because for sampling, the diversity of samples can be ensured, right? But the quantity, because we do not control the quantity. So also quantity, that's the how large is the objective functions, object function values, right? So because we minimize the function, we hope the function values should be improved. but when you do sampling, we do not have any control to the quantity, right? So then in this stage, we can introduce certain kind of local search. So here we call the field function. That means what's a field function is we define a neighborhood of the current solution, current point, and this neighborhood, the number of points in this neighborhood is very simple. Okay, number points is very small. Then, because the number is very small, we can do a grid search in this neighborhood and obtain the optimal solutions or approximately optimal solutions, right? And in this way, we can improve the quality of those points. Okay. And so how we choose the neighborhood, the different approaches. For example, we simply define the neighborhood in this way, because in this setup the function is the object function actually is if we simple, for example, quadratic, also it may not be quadratic, but can be. So the k points is so the subproblem can be minimized very efficiently. Okay, and then you can improve the quantity. Another type of thing you can do grid search, for example, local search. The simplest one you just flip the every bit of the solution. For example, change -1 to 1 and vice versa, change 1 to -1. And you can you can and go visit every indices of the point. Of course, there are many other variants of the greedy type of approaches. All of them probably can be fit in this framework. So in summary, after the sampling, we need a kind of process to improve the quantity. Okay, and then after improvement, obtain the refined points, and then then of course again we can update the advanced function and we repeat this process. And in this process, if the quantity of the object functions is very promising, of course we can stop. Okay, and we can repeat this process by a few iterations. Then we can find very good solutions. So we can we want to analyze the certain kind of theoretical performance of the algorithm, but it's very difficult because you see original problem can be hard. So how can we ensure us to find the good noble solution? This is almost impossible, right? But you can probably you can check our our publication. We have kind of theoretical understanding. Okay, but then today I will skip it. Let me show you a few numerical experiments. This is a classical max-cut problem. We try some kind of random graphs. We see for this kind of approach, it can be so the quantity actually is pretty good. And also we test this called G-set problem. This max cut problem, and the number of nodes actually is not huge. And the performance is quite competitive. In this scenario, we do not limit the number of iterations. We just run the algorithm sufficient large number of iterations, and for certain kind of problem, for example, for this problem, G17, we find a solution which has not been found in the literatures. So this is this is the idea of my foundational model. So the idea is so we for problems we can we can do sampling, because it's binary. Of course, we can design the sampling process very, very easily. But you may ask, how about if we have much more complicated scenarios? So let's check so-called routing problems. For example, this TSP with time window and this TSP with draft limits. Both of them have so-called hard constraints and soft constraints. So rather than the binary constraints, we have many other constraints. So this problem is actually is much more complicated. But again, we can apply similar idea to this problem. So what we say is, so we want to do sampling to sample the feasible solution. But of course, for this problem, because the constraints is much more difficult, so we split the constraints in two parts. Okay, so one is very easy. So in other words, we can ensure the feasibility during the sampling process. Another part is for those constraints are very difficult to be satisfied. Then we penalize those things to the objective functions. Okay, and hopefully we control the quantity. Okay. So this is in this way we have to modify our loss function. Uh, so previously in binary operation, the function we only have this one, right? The functions. But now we have a penalized terms, which is for those constraints are very difficult to be satisfied. Okay. And another time approach is this is still the same. This entropy time. Okay. Um, so well, then you may ask how we sample feasible solutions for those either constraints. So here is because this is a routing problem. The process is different. So suppose we know so suppose we have to visit a bunch of cities in a sequential way, and suppose we have visited the city number one, city number two, and until city number t, um, and given this particular instance of problem, and suppose the probability for visiting the t plus one city is not than zero. And suppose this probability is not than zero. Then we can do sampling. So how we do sampling? Because suppose we because we have no the t cities, right? 1 to t cities, and we sample t plus 1 cities. Then we simply plug the variable into the constraints to check whether if it satisfies the constraint or not. Okay, if it is satisfied, then it's okay. If the feasible solution, okay, it's okay. Okay, then we generate next location, the t plus 2 location. So suppose if the solution is not feasible, then we do backtracking, because we start for this one once again, and because the probability is not zero. Suppose we can do a sufficient number of sampling, and we know we essentially we can find a feasible solution. So that's a basic idea. So in this idea, we can just utilize similar masking strategy in large language model. This way we mask a certain kind of cities, and we do backtracking. Well, so what we name is the maskers. Okay, in this way, we can do sampling node by node. So, and then we can obtain the feasible solution with the quotation. So there are different strategy in the training process and the testing process. Because suppose the problem is very difficult. So certainly we do not want to spend lots of efforts in training, in identifying the feasible solution. Then we can limit the resources for the backtracking. So that's why in this process it may not be feasible. Right? In the training process, it might be feasible, but the penalized, it will be feasible as much as possible. So in this sense, it's very similar to the traditional algorithms. But in the testing, so suppose we want to solve a real problem, then we can repeat this process sufficient number of iterations to ensure the feasibility. Okay. So we have to combine balance training and the testing, and this is our framework. Okay, and I guess this kind of framework can be applied to different kinds of problems with structures. And let me show you a few numerical experiments. We do comparison with traditional solvers, for example, Pi, VRP, and LTH, and OR tools. These are traditional solvers, and the accuracy can be pretty good, but they may not be fast enough. So we generate 10,000 TSP-TW instance of with 100 cities. And if we try the traditional solvers, it will take more than 4 hours to solve all of those instances. However, if we try our learning algorithms, it will only take 20 seconds for all those 10,000 problems. And let's say how it performs. The first figure is the infeasibility. You see, the red one is our algorithm. You almost never see the red color. That means our algorithm is almost feasible. And this is the gap of the function values. Of course, you see the red color, but compared to the greedy algorithm, you see the greedy algorithm almost traditional one almost it's the gap is pretty good. But the time it will, you say, take 4 hours. And those colors corresponding to the learning algorithm. And for this learning algorithm, you see the gap may not be good. But for our algorithm, our strategy can be pretty smooth. And finally, let me tell you, for this problem, this is a kind of small foundation model because, as I mentioned, the function f can be example from different problem classes, right? And there are many different kind of routing problems, many kind of variants. And for example, for this framework, we can solve 60.
Капучино средний и давайте
Jim.
Yeah,
конкретно.
sure.
Yeah, sorry.
Any other question?
No, it's not a question. It's only about cappuccino.
Sure. Okay. Sure.
Sorry,
No problem.
sorry.
So I almost finished this part. Any question for this part? So what I go back. My key idea is I just gave you my solution, my foundational model for combinatorial problems. Is that right? Okay. Okay. Any question?
Maybe you have a demonstration just how it works to just maybe if we have if it's visible for the guys, yeah, it can be nice to understand what's going on, how what the generalization properties. Yes.
Yeah, you are right. But for our testing, so far you say this is very this is very difficult question. Of course, we always limit our testing on a given data set. We split the data into the training and the testing data, and for those data sets is pretty good. But of course, you say if we change another type of data set or even change the size of problem, probably the performance is not good. So I guess still there's not a known way to for those learning algorithms, but it's very promising. It's a new paradigm, and that's my that's my perspective. Okay. Mm.
And maybe a stupid question, and
No,
maybe
no.
maybe I just miss. What is the difference between, for example, the time for traditional solvers
Mhm.
and uh, here? This is traditional solvers for which problem? For the
For the
whole
routing
data
problem,
set.
for the routing problem,
Uh-huh.
for
Okay.
for this problem, those problems,
Okay.
for this problem.
Okay.
Mm.
Okay. Okay.
Uh, so the difference is for the traditional one, you say, for example, for autors, for example, depends on the algorithm.
Mm-hmm.
For example, it has the integer programming or the constraint programming. So these are classical traditional algorithms. They are based on either solving linear programming or do kind of search, right?
Yeah.
But
And
the most difference is for all algorithms, we design a neural network.
yeah.
Okay, and so the concept is we fit in the data and go through the neural network, and then we obtain the solution. So essentially, but of course you say so this is sampling process. We have to sampling in this way. Uh, because we want to we will construct a solution by this node by node process in this problem. But the idea is go through the neural network and then we obtain the solution. And another huge difference is for classical solvers, we have to solve the problem one by one. Okay. And for this setup, we can do it in parallel. Okay. Um,
And the question may be
in a
about
batch.
also for me,
Mm,
in maybe in my previous picture of the world, this fundamental
mm,
model can be nice if as a just starting point. And in your
yeah.
experiments, we see that it can be just enough to use it without any additional solvers. Yeah.
Mm-hmm,
Do you just maybe for the other problems you just use the combination? For example, your fundamental models plus
mm-hmm.
just classical solver.
Yeah, yeah, sure, sure. For example, we generate a very good initial point, and then we call the traditional solvers. Of course, this is a very good combination. Okay. Yeah, right. There are many possibilities. So let me give you another scenario. This is a scheduling problem. So this is another problem. If we solve the traditional mixed integer linear program formulation, is very complicated. But for the linear approach, we have to design new kinds of formulations. So the idea is we can do the sampling efficiently. We can also um, encode the constraints for the neural networks. Uh, and then we pass the solution, pass the data from the neural network, we can generate the solution. That's the most difficult part. So instead of consider the mixed integer linear programming formulation, we consider this one, sequential modeling. And this allows us to construct a neural network. And there are certain kind of details, but essentially we, we input the data and we generate the solution. And then once again the training process is very similar. Is essentially the same. Once again we can try the reinforcement learning approaches for this problem. And for a certain kind of data set, the performance is quite good. And finally, And let me show you another example. This quadratic ensemble problem. For example, there are different kinds of formulations. For example, X is a permutation. This is a square matrix, and each element is either to be 1 or 0, and each row has only one element to be 1, and each column only have one non-negative element. And the functions is quadratic, both f and d are given data. So how we solve this problem efficiently? This is of course this is a NP-hard problem, and then we construct a learning approach, a learning modeling. You see, this is function values. Small f is corresponding to the function. And so what we need is to construct the pi. So there are two kind of formulation. The pi just simply permutation of 1, 2, 3, and to small n is the random permutation, right? So given this permutation, so sigma is example of a given permutation. So it's a permutation, and this is essentially the function values. And for this one, we jump on different instance for different problem classes. So this instead of for one single problem, we do training for a problem classes. Okay. So how we do the neural network? We have two matrices. One is F and another is D, and we do different embeddings for those two matrices, and they construct a certain kind of graph neural networks, and then it will generate given after a certain kind of header map, and we generate a permutation. So this is architectures, and all other things are the same. Okay, we just like we compute the Poynting gradient, and then we do the updates. So here is we do on the synthetic data and also on the QAP9 for this data set. The performance is pretty good. So this is our performance of our algorithm. So either this the average gap on the average time. You see the average gap. The gap is quite small. And we also test on this data set. For this data set, you say is you say the performance also is very good. So this one, this is traditional gradient search algorithm, and the Plama is our algorithm. You see that the gap is kept in a very low level. So all right, this is our algorithm. So let me go back to the generalization question once again, and let me go back to this figure. So this the pipeline divided to two parts. Actually, is the learning part, and also this part is the sampling process. You already mentioned how well. So suppose if this data set has not been sampled, right, has not been trained, can this algorithm, can this process also perform pretty good on this kind of data set? So my answer is for this part itself can be an independent algorithm modular. That means after the learning process, you obtain initial solution. You can refine the solution for this sampling process, right? Suppose we have obtained very good initial solution. We just what we do is just do sufficient number of samples. So this is called a refinement. So in our practice, actually the refinement process actually is pretty important. Okay. is pretty helpful. So this part I finish this part for this part is for this foundation model. So any other question? If not, I can move to another one for which totally different. Let me go. So formalization and automatic self-improving. In this part, so what we want to do is we want to prove things automatically. Let me give you an example. So this is a gradient type method for this unconstrained optimization problem. And suppose the function is convex, and suppose the gradient is nilpotent continuous, then we know after k iterations, the function values, the difference of the function values is 1 over k. That's a theoretical analysis, right? So how we understand the algorithm, how we understand the convergent theoretical analysis. Can we describe the algorithm in a piece of code? Of course, different from the numerical computation. Numerically, what we do is we have given the functions and given the point xk and evaluate numerically. But now my question is, can we understand the algorithm, describe the algorithm in an abstract way, just as our human to understand the algorithm? So this is a description of the algorithm in a piece of code. This is called formalization, in particular in the so-called Lin language. Okay, and because this is also the corresponding part of this statement, theoretical analysis. You see, so this is corresponding to the algorithm, and this line corresponding to this statement. You see there are many small parentheses, those are assumptions. Okay. So suppose we have translated all the theorems and the theoretical analysis in human history. For each statement, for each theorem, we can obtain this kind of translation. And for this translation formalization, we can verify the correctness of the algorithm if the theoretical analysis by a piece of code, because the compiler behind this formulation it will verify this theoretical result. Suppose it can pass the combination, then we say the theorem is correct. Okay. So over the last few years, we have do this for optimization. We have built up a library for optimization algorithm. It can be checked in this GitHub link. Okay, and we have opened many training sessions. Let me give you an example. We have formalized a book by Professor Rockefeller, the so-called convex analysis. So this is a statement in the book. Okay, and this is a translation to the formal language. Okay, and after translation, after we have done, we will say we build a web page for both the description in the natural language, also in the formalization language. And suppose I just mentioned to you, suppose we can do this for all the theorems in human history, then probably can we do the automatic theorem proving? So I myself is quite optimistic. Actually, during the last few weeks, you can say many progress. Okay. So, but comparing to the proof in natural language, the most powerful thing, the powerful of the formal language is verification, right? We can do the verification. We no longer depend the human to verify the theoretic results. They can do it by the computer language. This is quite significant. And how we achieve this goal? We develop a pipeline. So we first translate the PDF file to a LaTeX file. and we extract every definition, every statement, every lemma, every proposition, every theory into a not-take file, which of course we put it in a JSON file. And then we translate the statement from the human language to the formalization language. And for those two steps, translation PDF to JSON, also translation from human language to formalization, this has to be checked by humans. And after the stage, for the proof itself, we do it automatically. For example, it can be performed by codecs. Of course, we have written very careful prompts. We have to do very careful prompt engineering, written more than 10,000 lines of code prompts in this process. Particularly for my student, Zhiseng Wang, he has turned his human knowledge of formalization into this prompt engineering, and it's very. I think the performance is pretty good. You can check the details in this link. Also, the source code of those books can be found in this link. So we've also formalized a book by David Tao in NS2. So I think it's I think it's very interesting. So let me try to show you some examples in what is the formalization. Okay, so we build up a web page. You can try it in this one. So this is a formal. This is a released version of our web page, and of course we have a beta version. Let me switch. How we switch to? Yes, no, just a moment. Yeah. So you see, it's this formal language, suppose, and so this statement of the algorithm, statement of the statements, okay, of the theory, and this proof, right? Once it's been proved, then it will show goals accomplished. Okay. So I'm not sure if the audience, if you have do you ever written this kind of language? If not, you can try. For example, this I've test. Let me ask the inversion. This is input a large language model. Ask so please explain those codes in Russian. You see, for this statement, explain in detail. Yeah, yeah. You see. Of course, you can ask copy and paste to other large language model. It will explain those definitions to you. And we can also do automatic serial proving. For example, this story, the proof is not being, so this one is not being solved. So let me add to chat and please, please verify this. This sorry. So they will do it automatically. Okay. So it will take some time, and it will pass the combination. So you see, once they come to this is called the info view. Just like a human, we do proofs line by line. This it will show you the result in the proving stage. Okay, it will take a few seconds. Anyway, after so I'm sure it will solve it automatically. So I just mentioned, suppose we have formalized all the series in the human history, so probably we can do automatic seven proving. So so that's my goal. Okay, and many mathematicians, also the big companies like ChatGPT, as I guess almost major companies like Claude and Google, all of them have do this kind of research. Okay. So I guess I will stop here. So any question from the audience? So if
Yeah,
you
maybe the question, do you hear about the PEP package by Adrian Taylor and other guys from France? This is also about the proof. This is performance estimation, and this is
yeah. Mhm.
yeah. You hear, yes?
Yeah.
Yeah,
Yeah. It's
yeah. And
different.
my question is, how can maybe it's quite old for the current situation, but it's nice to find the worst case in terms of the convergence. And the question is, maybe you just think about how it can be used in the at the current your tools, because it can be nice to find this convergence, the hypothesis of the convergence, what your tool can try to prove. Yeah, this is just a question, uh, or maybe
Yeah. So
suggestion. Yes.
yeah. Thank you very much for the suggestion. So the formalization is different from the PEP. So the
Yeah,
formalization
of
is
course I understand. Yes, I understand.
yes. But of course, we can also apply formulation to PEP. Just do translation, or we can combine those two things together. So probably is very interesting.
Yeah, yeah. Uh, guys, don't shy more questions.
Yes, I have a question related to automatic theory improving. I see like two alternatives. First is like reasoning on human language. It is really hard to verify, but human languages proof can be really short, while Lean reasoning it's can be verified precisely. However, the proofs are really long, and it means that there is a really huge search space. And my question is, can we use these trade-offs maybe to combine these two strategies, two ways?
Yeah. Of course. Exactly. I think so. If you see most recently, those breakthrough actually most natural language, because I think the main reason is the source of natural language is much more than the formalization. Okay. So because those natural model have I think have written have know all the human literatures in the history, right? And they know all of those things. Um, so they are very good at trying new things or trying different kind of proving stages. For example, for a conjecture which have never been solved. In the natural language, they probably can provide a certain kind of way to do the proof, and then probably for human being checking those proofs, whether it's correct or not can be very difficult, right? And then another advantage is probably the human only point out a certain kind of possible way, but they don't know the, but they do not provide the detailed proofs because doing this so will be very time consuming, right? And they have to do a lot of computation and have to verify many things. But once we have all those kind of things in formalization, so probably verify those ideas can be done by combination of AI and the formalization. And this way, then the check if this statement is correct or if this way is correct or not. And in other words, we can combine those two different approaches, right? And the natural language, the natural language model in natural language, they can propose different ways for the proof, and the formalization, they check the correctness. So probably in the future, I believe many students in the audience, you have a submit your paper for certain journals and a conference, right? I think it's a painful process for waiting the decision because most of the time the people have to understand your proof, but in the future the correctness of you sharing your statement is no question. All things are correct. All the people need to do is verify the novelty of your statement. So, so probably in next 10 years or 20 years, I think mathematics will be changing a lot. Okay, thank you very much for the question.
Hello.
I have a
Would you also have a question?
Recording in progress.
Would you please share the results for scheduling?
Excuse me?
Could you please share the slides where you showed the results for scheduling?
I think
Scheduling
it's
problem.
traveling salesman problem rather than scheduling.
For this one, this is another work. We published a paper in 2005, so it's very interesting. So mathematically, let me see. Yeah. So, so for example, so my background is in mathematics, and we develop a certain kind of very general algorithm uh, for solving many types of algorithms, right? For example, in this example, we solve a non-smooth problem, and this non-smooth a particular instance is for this one called the Nassau problem. And there are many applications in imaging process and many other areas. And for engineers, those people do not care about the proof. But if you say, for example, in IEEE transaction on signal process, people still like proofs, right? What people do in those proofs, probably they only check whether the conditions are satisfied in the general setup. And this can be checked easily. So in those two columns, there's a formalization of the general algorithm, and in the last column, this for this particular instance, then we can do automatically proving, right? So to just apply the abstract theorem to a particular instance, we only need to verify the assumptions, and you say if you have not you never know the Lin language, so those code can be very difficult to be read. And then again we can translate the Lin language to formalization language to human language. You say then the theoretical statement can be understandable. So we just do this simple work, but the idea can be generalized to more deep mathematics. Okay, thank you.
Could you please return to the slides with scheduling problem with results
scheduling.
on this? Yeah.
For scheduling, for this one, is this nice? You want to see?
I think we want to see the results. I mean,
next slide.
yeah.
Next slide.
Oh,
the next one.
results. This one? This one? Let me see.
Yes, this one. Do you compare your results with the iterative scheduler?
So this is traditional approaches, and those are learning methods, and those are our algorithm. And there are different two data set, TPS-H and this Centric data set.
What does triple time mean?
Which
In the first table, the second row,
Stable.
the second
Second
column,
row. Second column.
yeah.
Yeah.
What does it mean?
Sorry. I'm not sure whether it's a computational time or not. You can check it either. This be done by my students, probably the computation time. The computational time. For example, to
Okay,
solve.
thank you.
Yeah. I think it's a computation time. You see, for the gradient approach, the speed is very far. It's very fast, but the function values is much larger than our algorithm. You see, and for those linear algorithm based PPO, the time is longer, but for our algorithm, so the time is much shorter, and the quality is still very good.
Okay, thank you. Yeah.
Thank you.
Okay, another more question about this table. I see that the time of your solution is much more than time of the solution of the basic solver. However, maybe you find some trade-off between time and the quality of the solution. If you run the solver for the longer time, maybe it can reproduce the quality of the solution of your method, or not. Either is trade-off.
Pardon me, can you repeat the question once again? The last
Yeah,
part.
of course. I see that the time of the solver, of the basic solver, for example, Heft or Tetris or another, is much smaller than the time of your solution. But the quality of your solution is much better than the quality of the solver. Maybe we can find some trade-off. I mean, we can run solver for a longer time, and the solution of the solver increases or not. No, this is my question.
Actually, I've asked my student to run those algorithms in longer time, but I think it's still not competitive to our algorithm. Yeah, but I think
Okay.
yeah.
Okay, that's great. Okay, thank you.
Yeah, guys, more question? More?
I have one question about frontier improvement and discovery pipeline. So, what's your perspective on next decade? How should a scholar or a novice or even a PhD in fundamental mathematics should plan its research using such instruments as the Lean and automated improving by reasoning? So how could they contribute there, or what should they try first in order to improve their, for example, their either understanding of the field or their, let's make it a question more practical, their publication activity as well?
Oh yeah, this is a very good question. So actually, if you test, if you try our website, actually, let me show you. This so essentially those two websites are the same. Let me see. Sorry. Let me try this beta one. Yes. So we built certain kind of agents. This one is with no copilot. It can generate the papers automatically based on very simple input. So so my idea is, you see, we have almost everything prepared, but we have not combined it together. So this one is writing papers in natural language, okay, and it can produce pretty good papers. I think for some of them, it now is publishable in certain kind of SCI journals. And then, as I just showed you, we can also do formalization, right? So in the future, I will combine those tools together. So what does it mean is we can write a paper in natural language. We can also even ask those agents to generate the paper, and they will verify the correctness by the language. And probably after 5 or 10 years, we can solve open conjectures in this way. Yeah, I think for your question, back to your question, I think this. So if this is really possible, it will be a great challenge to many mathematicians, right? Yeah, of course, even for myself, because for myself it's okay. I'm going to retire in 10 or 20 years, but for our students, what will they do in the future? But from my perspective, they will do much better mathematics. For example, taking my field is operation research. I'm not sure what's the situation in Washington, but in United States, I got my PhD at Columbia University. It's in the engineering school. Almost no optimization people in the Department of Mathematics. Optimization has transferred from mathematics to engineering to B school, and so on and so forth. So I think in the future, probably this is the same way for pure mathematicians, right? So there are certain kind of fundamental problems. So what they do today, the pure math, they study. So what's the problem? The problem is applied mathematics problems in 20 years ago or 200 years ago. So in the future, what's the pure math problems? Probably is those problems we studied in artificial intelligence, also for no operation research in practice, right? Of course, we have not solved many fundamental problems. We always invest in we always in, find new ways, new technologies, right? Like those technology to run the Nobel Prizes. I think those will be a source of problems for applied mathematicians and for pure mathematicians. So, so of course we have to. So this is a challenge for students. They have to name more things, name more fundamental things. And my suggestion is for students, they have to learn pure math courses on pure mathematics, also courses on computational mathematics, and the courses on machine learning, and for those fundamental things. Whichever is the learning paradigm is changed, they will they will still survive. Okay, so that's my perspective. I'm still quite optimistic.
It's good. Maybe the last one as a cherry on the top. What do you think about paradoxes? Some in computation, something like Turing completeness or self-applicability problems. Will it break this framework, or we will find some workaround there? Something from logic and computation.
I don't know. I don't know.
Because the machine theory
Mhm.
or computation sense that we have some theoretical limits, and where is the bound between the limitness of our ability to compute and the limitness of our understanding in terms of mathematical for foundations. Axioms.
So I trust you guys. I trust you guys are genius, are smart people. Probably you find new ways, new technology. For example, we travel by train, travel by plane, and travel by rockets. Right? If you limit your perspective in the train, you don't say how fast we travel by plane or by rockets. So probably you mentioned that those limits they are not the issue for a new kind of technology. So who knows? Who knows? I don't know.
So we'll discover. Thank you.
Yeah. I believe in the discovery in the future.
Yes, and may I have another one question? Do you see the autoregressive nature of LLMs like a bottleneck for automatic theorem proving? Because one wrong token can ruin the further trajectory of the proof, and maybe some diffusion-based text generation or some MCMC additional improvements on top of LLMs can enhance automatic theorem proving.
Yeah, this is a very good question. And actually, I don't have this answer, but I do think probably there are limits on automatic theorem proving. And can you just imagine can human solve the many open conjectures, for example, remaining conjecture and so on forth, right? There are many open problems which has not been solved. I'm not sure whether there will be an upper bound of our technology. I'm not sure. So probably we need to invest. Probably we have to find a new kind of mathematics, more new foundations of pure math. I'm not sure. So probably in the future, the NIN is not the only way, or NIN or the formalization probably itself is it probably is not the best way to do automatic theorem proving. But currently I think this is it's a good practice. For example, we have to digitalize our human to digitalize the mathematical literatures, right? So over the last over hundreds of years in mathematics, we never take advantage of technology, right? So just like a relationship with the students and your advisor, it's like a son and to a father, right? Like we have to train the student hands by hands. But you see in other fields like biology or other fields, physics, many fields that they have taken advantage of the technology. So I believe formalization is a way to advance the research tools of mathematics. This is very important. And probably even if it's the first step, it's a revolutionary step. Thank you very much for the question.
Yeah, thank you very much for nice speech, and you see that a lot of questions because it's quite hot topic and very interesting for our mathematical society here in MIPT. Yes. Again, very happy to see you in our seminar. Yeah.
Me too.
Thank you again.
Much.
And yes.
Thank you much.
Yeah.
So by the way, are there are there another discussion in
Yeah, let us change the link. Yes, let us change the link. Yes.
Okay. So they are quite
Yeah.
very
And in
small.
Russian. Спасибо всем, кто присоединился. И увидимся на следующем семинаре. Yeah, thank you.
Thank you.
Yeah, thanks a lot.